So unfortunately, due to some technical difficulties, I'm going to have to re-record the second video on electrochemistry. Let's first begin our discussion with a brief review of spontaneity. Remember, spontaneity means that we will convert over 50% of our reactants to products. So it doesn't mean that a reaction goes or doesn't go. It simply deals with the yield of products relative to reactants. And when we discussed thermodynamics earlier in the semester, one of the main indications of spontaneity is that we have a delta G value that is less than 0. We introduced two such equations for measuring delta G directly. One is delta G as a function of other thermodynamic functions such as delta H and delta S. And we certainly use this equation a lot in Unit 1 to solve a multitude of thermodynamical problems. Also, we can express delta G as a function of the equilibrium constant, which is minus RT times the natural log of the equilibrium constant, big K. And now that we've done kinetics, it's important to distinguish big K from little k. In this case, R has a value of 8.3145 joules per mole Kelvin. And so this is the value of R you use with any kind of thermodynamical system or any kinetic system, like when you're using the Arrhenius equation. There is, however, a third function for delta G, and this relates to electrochemistry. We are going to express delta G as a function of electrical potential. So delta G is equal to minus N F E standard state. Of course, this delta G is a standard state. This delta G is a standard state. This one, however, is not. This is derived from the law of mass action when the delta G of the standard state is equal to 0. So let's talk a little bit about some variables in this equation. N is the number of electrons transferred in a redox reaction. And we need to define this very carefully and very specifically. And let me also amplify, when I say number of electrons, I'm talking about the number of moles of electrons. So let me illustrate this with just a simple example. Let's consider a process in which I have two half reactions. One is MnO4 minus going to Mn2 plus. Now, in order to balance this equation, I got to balance the number and types of atoms. So I'm going to add 4 water molecules to the product side, which means I need to add 8 H plus ions to the reactant side. And then to balance the charge, I need to add 5 electrons to the reactant side. So notice that I have a +2 charge in reactants, a +2 charge in products. Number and types of atoms are all balanced. Now this is the reduction half reaction. Let's say for the oxidation half reaction, we have zinc that is oxidized to zinc 2 plus 2 electrons. The number of moles of electrons that are transferred in such a process is going to be the least common multiple of 5 and 2. So the number of moles of electrons transferred in this reaction would be 10 moles of electrons. This is what N is equal to. Let's talk about the variable F. F is actually a constant known as Faraday's constant. And Faraday's constant deals with the amount of electrical charge that is required to react with a mole of electrons. Usually this deals with the reduction of a mole of electrons. So electrons would be a reactant, but it could also be applied to where electrons are a product during oxidation. So this amount of charge is 96,485 coulombs per mole of electrons. And we're going to see how this becomes important when we look at Faraday's law application, and really that will be the last thing that I cover in this particular video. Let's talk about the sign of electrical potential needed for spontaneity. I think that's pretty important criteria. That's certainly covered on your final exam. So delta G must be less than 0. Delta G is equal to minus NFE, standard state. Therefore, E standard state for a spontaneous reaction must be greater than 0. Very important criteria. Let me illustrate this with an example. So let's look at a couple of reduction potentials. Let's look at auric 3 plus, better known as gold 3 plus 3 electrons being reduced to gold. And the reduction potential for this process is 1.42 volts. Let's also look at silver plus 1 electron being reduced to silver. This has a reduction potential of 0.79 volts. There are two possible reactions between these two systems, one of which would be Au 3 plus being reduced and silver being oxidized. And of course, if you look at the charge very quickly, you realize that we need 3 silver for every 1 gold. So that's a balanced chemical reaction. Or the reverse reaction is a possibility, where we have 3 Ag plus Au, which yields Au 3 plus 3 Ag. We can use these reduction potentials to predict which of these two reactions will be spontaneous. Simply what you want to do, for the first reaction, we would want to keep the first potential the way that it is, but we would want to flip the second one, which is going to flip the sign. So in this case, we're going to get an electrical potential that is going to be equal to 0.63 volts. So on the bottom reaction, you'll get an electrical potential of negative 0.63 volts. We want to choose the positive one, therefore the top equation will be the spontaneous reaction. One of the major differences between a galvanic or a voltaic cell and an electrolytic cell is one of energy conversion. So in a galvanic or voltaic cell, galvanic or voltaic. Remember, these were both named after two founding fathers of electrochemistry, if you will, Galvani and Volta. In a galvanic cell, we will have a spontaneous reaction and we're going to convert the free energy in that spontaneous reaction to electricity. We will produce a current. In such a process, the electrical potential must be greater than 0. The delta G must be less than 0. All right, so the other type of cell that we encounter is called an electrolytic cell. And as its name implies, we are going to use electricity to lyse a compound. So we will take electricity. This electricity is usually in the form of a battery. And it will provide a voltage to convert this electricity to a spontaneous chemical reaction. The reaction itself is not spontaneous without the extra energy source. But this extra energy source in the form of electricity is used to generate chemical products. For this process, the electrical potential is less than 0, while the delta G is greater than 0. The reaction isn't spontaneous because delta G is less than 0. It's spontaneous because I add another source of free energy, if you will, in this way in the form of electricity. Now, a couple of differences between these cells. One is going to be the way the current flows. In the galvanic cell, the current is going to flow from the anode to the cathode. So in a galvanic or voltaic cell, the current flows from the anode to the cathode. In the electrolytic cell, because of the presence of this battery, the current flows in the opposite direction. It flows from the cathode to the anode. In both cells, the oxidation occurs at the anode. In both cells, the reduction occurs at the cathode. There is no difference in that regard. But the flow, the direction flow of the electrons in the cells is different and should be noted. Okay, so now that we've discussed introducing what Faraday's constant is, we've discussed delta G equals NFE minus NFE. Let's talk about for a moment the Nernst equation so that we can discuss how the electrical potential can change when pressure changes or when concentration changes. So the Nernst equation is actually provided for you on your equation sheet, and I'm going to give you the exact same form that is on your equation sheet. And it is simply the electrical potential at any concentration or any pressure is equal to the standard potential that we would get off of a chart of reduction potentials minus RT over NF times the natural log of Q. Remember, Q is that reaction quotient where Q, much like the equilibrium constant, is the concentration of products to their stoichiometric coefficient powers over the concentration of reactants to their stoichiometric coefficient powers. Remember, and let's just look at the simple system of zinc metal plus Cu 2 plus ion that is converted to zinc 2 plus ion plus copper metal. Q for this process is going to be the concentration of zinc 2 plus divided by the concentration of copper 2 plus. In a more general sense, and of course this is subject to change when the complexity of the system changes, the concentration of ions or gases at the anode divided by the concentration of ions or gases at the cathode. This is a pretty simple system, so I'm going to refer to this in terms of zinc and copper proper. Now we know that this system has a standard electrical potential of 1.10 volts. Let's look at a couple of different situations. First, I'm going to go ahead and finish the equation. R and T and N and F are going to be constants for a given system. So what I want to change is a number of parameters. So in the standard electrical potential, all solutions are assumed to be 1 molar, and all gases are assumed to be at 1 atmosphere. So why don't we look at what happens to E as compared to this 1.10 volts, which is what it would be when I use 1 molar solutions, if I dilute the zinc solution by, let's say I dilute it to 0.1 molar. And we're talking about diluting the zinc solution. Let's also look at what happens if I dilute the copper 2+ solution to the same, to 0.1 molar. Finally, let's look at what happens if I dilute both solutions to 0.1 molar. So let's go back to our equation. If we dilute zinc 2+ to 0.1, this fraction is going to decrease. Okay? In fact, I will be taking the natural log of a number that's less than 1. By the way, what that means is if I take the natural log of a number that's less than 1, it will be negative. A negative times a negative is a positive, and the electrical potential will be greater than 1.10 volts. If I make the numerator smaller. Now also, mathematically we could do this. It doesn't make a lot of sense to do this in the lab. I could concentrate copper 2+. The only way you're really going to be able to do that is to add solid copper sulfate to one of your cells. It's a lot easier to envision diluting. You're just going to add some water. But either diluting zinc or concentrating copper will increase the electrical potential from its normal standard value of 1.10 volts. Let's look at what happens in the second process. If I dilute Cu2+ to 0.1 molar. So this becomes larger and this becomes smaller. And I just see a mistake. So let me go back and restate my claim on this. So let's go back to the first one. Sorry about that. Sometimes it happens. So if you dilute zinc to 0.1 molar, this becomes smaller. This will be negative. Negative times a negative is a positive. E is greater than 1.10 volts. Diluting the top is the same as concentrating the bottom. So let's say we left zinc at 1 molar, but we concentrate copper to 2 molar. It's still going to be a fraction that's less than 1. The log will be negative. E will be greater than 1.10 volts. Okay, let's look at the next scenario. If I dilute copper 2+ to 0.1, now 1 over 0.1 is 10. This log will be a positive number. I will be subtracting a positive number from 1.10 volts. In this case, E will be less than 1.10 volts. I can accomplish the same thing by concentrating zinc. So rather than 1 and 0.1, let's say it's 2 and 1. The natural log of 2 is going to be a positive number. I'm subtracting a positive number from 1.10. E will be less than 1.10 volts. If, however, I dilute both or concentrate both to the same value, E will be equal to 1.10 volts. These three scenarios are very important. You will have to address this on your final exam tomorrow. All right, the very last thing that I want to do is to look at a Faraday's law problem. This was common in the automobile industry when bumpers used to be made of things other than fiberglass and styrofoam. So let's look at an example of, we have a 20 amp source of electricity, and we are going to allow this this current. By the way, an amp is equal to a coulomb per second, which we'll need for our dimensional analysis. For 10 minutes, we're going to allow this current to run in a cell where zinc 2+ will be completely reduced to zinc metal. That's not a spontaneous reaction, so I'm providing electricity to plate zinc. The question is, what mass of zinc will I plate at this current for this amount of time? This essentially becomes one grandiose stoichiometry dimensional analysis problem. We'll begin with time, 10 minutes. Since current is coulomb per second, it only makes sense for us to convert this to seconds. So our first conversion is going to be that 1 minute is 60 seconds. And we can cancel minutes from our dimensional analysis setup. The next conversion will be one of the current. We have 20 coulombs per second. Now seconds neatly cancels. Now we're ready to use Faraday's constant. Remember, Faraday's constant is 96,000, wrong color, 96,485 coulombs will reduce 1 mole of electrons. Again, coulombs now cancels. And the important thing about Faraday's constant is it takes us from the experimental data, the time it runs for, the current that is present, into our balanced half reaction. Because now I know that 2 moles of electrons will produce 1 mole of zinc metal. Now moles of electrons cancel. Almost done. And of course, 1 mole of zinc is 65.39 grams of zinc. Moles of zinc now cancel. I have my answer in terms of units in grams of zinc. So now all that remains is to simplify this monster expression, and when we do this, we find that we will obtain 4.07 grams of zinc. So just to recap the types of problem solving that you will be required to do on your final examination as it relates to electrochemistry. I said there are 9 questions. 1, you need to find oxidation numbers given a compound. The example I used in class yesterday was manganese, well actually permanganate ion. Find the oxidation state or the oxidation number of manganese. You should be able to describe electron flow in a galvanic cell and in an electrolytic cell. Don't do this to me. You need to describe electron flow in a galvanic cell and an electrolytic cell. Number 3, you need to be able to determine how many moles of electrons are transferred in a process. Number 4, what criteria have to be met when you balance a redox equation? So we'll put balancing. Number 5, what is the relationship between an oxidizing agent and the process it undergoes? What's the relationship between a reducing agent and the process under which it goes? Number 6, if you are given reduction potential data, determine an equation that's either in a galvanic cell or an electrolytic cell. You also need to, for number 7, you need to be able to use a Nernst equation, just like we did earlier in this podcast. You need to know the relationship between electrical potential and delta G in a spontaneous and a non-spontaneous process. And finally, you need to be able to handle a Faraday's law electrolysis problem. So that concludes everything that we need to know about electrochemistry leading up to your final tomorrow. Best of luck. I will be in my office this afternoon, and I also plan being in my office at 8 a.m. tomorrow if you have any last minute questions. Remember, tomorrow, do not bring your books, do not bring your notes. Bring your Scantron, your calculator, a couple of pencils. I'll provide everything else. Good luck.